Okay, so we're going to look at some calculations involving Avogadro's number. Okay, something called Avogadro's constant. But the key thing is that at 1 mole, it states that 1 mole of any substance contains 6.02 times 10 to the 23 particles. Okay, so we'll start off with some really nice simple ones, and then we'll kind of work our way up into a few more difficult ones, and ones that I've seen crop up on exam papers that catch students out. So let's take a really nice simple one to begin with and say, let's say the examiner says how many, just use capital P for particles, how many particles are there in 1 gram of hydrogen gas? Well, the first thing we'll need to remember is that hydrogen gas is diatomic, okay, so it's H2, so therefore it has an RFM of 2 grams. Okay, the next thing we need to remember then is that number of moles is equal to mass in grams over the RFM in grams. Okay, we then need to be able to convert between that and the fact that number of particles, we'll call that P, is equal to N, number of moles, okay, multiplied by Avogadro's constant. Okay, so you need to of course know both of those and then be able to convert between the two to get yourself your answer. So how do we do this? Well, we want to get particles. In order to get particles, we've got to get moles. We know Avogadro's constant already given to us, okay, or we just know it off the top of our heads. So if we do moles of hydrogen, of course, is moles equals mass divided by RFM. Okay, so obviously it's 0.5. Okay, so moles is 0.5. Avogadro's constant is 6.02 times 10 to the 23, of course. So we have 3.01 times 10 to the 23, okay, particles. In this instance, that particle would be molecules. Now, if the examiner here asked us about atoms, that'll be a slightly different kettle of fish, because every hydrogen molecule, okay, contains 2 hydrogen atoms. So if we wanted to convert that into atoms, if that's how the question was phrased, it would be 6.02 times 10 to 23, and this time it would be atoms. But again, that's up to you to read. I'll have said that the first part here maybe it was molecules, and the second part then they may have asked you for atoms. So anyway, that's as simple really as you can get. I'll get rid of that and we'll crank it up a little bit. So let's say this time how many atoms of magnesium in let's say a piece of magnesium which is 60% pure with a mass of 45 grams. So we've got this 60% purity to deal with this time, which adds a little bit of a twist to it, but not that big a deal. Right, so if it's 45 grams, 60% of it is magnesium really, well then all we're doing is finding what mass of that is actually pure magnesium in there. So 0.6 times 45 will give us, so actually 27 grams of it is pure magnesium. Okay, and then if we do 24 divided by the 27, okay, so 24 over the 27 is 0.889, okay, and that is moles of magnesium. And now we're in the moles, we take that and multiply it by Avogadro's constant. Okay, and that gives me very simply 5.35 times 10 to the 23 atoms of magnesium. So just a little extra twist in there, but nothing that should cause us too many difficulties, I don't think. Okay, let's take then something like we'll take ammonium sulfate. This can cover quite a lot of bases. Alright, so when let's say we've got 32 grams of it, and the examiner wants to know first of all how many what we call formula units. Okay, not a very often used term. So formula units, okay, the formula unit is just the entire thing. Secondly then they might ask, well, okay, how many ions are in it? Thirdly they might ask how many atoms are in it, and they might ask all three of those, or they might ask just one. Okay, so again the first thing we've got to do is work out how many moles of this we have got, and we need to get the RFM of this. So if we just first of all work out the RFM, that's 132 grams, and we would need to take our 132 or 32 and divide it by 132, and that will give us our moles. So 0.242 is the number of moles of this that we've got. So formula units, which is just the whole thing, if we've got that number of moles of the whole thing, then in terms of formula units, okay, we just take that and multiply it by Avogadro's constant, and that would give us the number of formula units, and that works out at 1.46 times 10 to the 23. Okay, ions are a little bit more difficult. Okay, well this is made up of ammonium sulfate, so it's got ammonium ions in it and sulfate ions in it. Okay, we need to be able to just work that out as A-level chemists. That would be expected of us. So we have 2 ammonium ions and we have 1 sulfate ion. So if that's the number of formula units, each formula unit contains 3 ions. So all we're doing there is taking that value and multiplying it by 3 gives us 4.38 times 10 to the 23, and this time we're working in ions. Okay, then it asks us for atoms, so we've really got to just work out how many atoms we have in a formula unit. Well, we have 2 nitrogens, and we've got 8, 2 times 4, 8 hydrogens of sulfur, and 4 oxygens, so we've got 10, 11, 15 atoms. So if that's the number of formula units, and we've got 15 atoms per formula unit, then we end up with 2.19 times 10 to the 24 atoms in there. Okay, so again, nothing too difficult about that. I'll have a look at another one. Okay, so this time let's change tact a little bit and sort of perhaps work back the other way. Let's say we have a sample of, let's say, potassium dichromate. Alright, and we have let's say we've got 7.5 times 10 to the 24 particles of it. Okay, then the question might come, how many oxygen atoms would be in that sample? Okay, the question might also come, what mass of sample do we have? Okay, I'm just trying to think of ways that the examiner might sort of twist around these questions to challenge you. So let's go first of all, well, how many oxygen atoms? So we've got this number of particles stroke formula units. Okay, so the whole thing, we've got that number of those. Well, so the key thing that we need to work out here is that every one of those has got 7 oxygens. So all I've got to do to work out how many oxygens there are, or how many oxygen atoms there are in a part in this number of formula units, is take that and multiply it by 7. Yeah, so it's no more tricky than that. Okay, gives me 5.25 times 10 to the 25 oxygen atoms. Okay, what is the mass of the sample? Well, in order to get mass I need moles. Okay, I've got particles. Okay, so I can get moles because particles divided by Avogadro's constant. So if I take that value there, so there from up here, divided by Avogadro's constant, okay, so okay, gives me 12.46 moles, and then all I do from there is I got mass, and I multiply that by the RFM of potassium dichromate. Alright, so that gives me multiplied by, I'll just do this, plus 39 plus, okay, and if I punched everything into my calculator right there, I would get 3.66 kilograms, 3,662 grams is what I have. Looks about right. Okay, fairly heavy compound, quite a lot of moles of it. Okay, I would expect a fairly large figure there. Right, let's have a look then. We'll do another couple here. So sometimes they will give you something like, let's say I've got sulfuric acid. Alright, and I've got, let's say, 0.5 molar sulfuric acid, and we've got 200 cubic centimeters of it, and then the question will come, how many hydrogen ions will that produce when dissolved in water based on full dissociation. So if we're going to work out slightly differently this time, so number of moles, N equals C multiplied by V over 1,000 of course, so C is 0.5, or V over 1,000 is 0.2, okay, so put that in there, so 0.5 times 0.2 gives me 0.1 moles. So a lot of people will go, okay, well if I have that, if it's a strong acid in full dissociation, that's how many moles of H plus ions that I would get, right? And they would take that and multiply that by Avogadro's number to give you particles of the hydrogen ions. But what you might fail to remember is that sulfuric acid is a diprotic acid, okay, so for every one of those sulfuric acid H2SO4 molecules there are 2 hydrogen ions produced, so the moles of H plus ions is actually 0.2, and that's what you should multiply by Avogadro's number. Okay, gives us a value therefore of 1.2 times 10 to the 23. Okay, so it's a fifth of that, and you can see 0.2, a fifth of that. Not always check your answer, guys, and look to see if it sort of looks reasonable, and hopefully there it does look reasonable. Okay, I think I've covered most bases there. I can't think really of, in fact I'll do one more. There's another one that might crop up on occasion. Okay, so if we take KMNO4, and let's say perhaps the examiner tells us we have got 8.3 times 10 to the 25 oxygen atoms. It's kind of similar to the one I did a few minutes ago, but a little bit more complicated, but it's just a variation on it. Oxygen atoms, and then they ask you what is the total mass in grams of the sample of potassium permanganate KMNO4 that you started off with. Alright, well, so that's how many atoms of oxygen we've got in it. So we've got to get, really, in order to work out the mass of this, we've got to get moles of this times the RFM. So I've got to go from oxygen atoms to moles of potassium permanganate. Okay, so I've got particles over here divided by Avogadro's gives me moles, which will give me moles, remember, of oxygen atoms. So, okay, so if I take that and I divide it by Avogadro's number, that gives me 138 moles of oxygen atoms, yeah, and that's kind of reasonable. It's a big number, but remember we're 8.3 times 10 to the 25 divided by 6.02 times 10 to the 23. Now, in potassium permanganate, every one of those has 4 moles, 1 mole of this, has 4 moles of oxygen atoms, so I need to take that to get moles of my potassium permanganate and divide it by 4, so that gives me 34.5 moles, and that's now where I want to be, moles of potassium permanganate. The RFM, the mass equals moles times RFM, of course, so if I take this and I times it by the RFM of the potassium permanganate, okay, gives me 5,446 grams. I would probably express that as 5.45 kilograms, and that's probably in around where you'd expect. You'd expect a large mass here because you've got a lot of moles of oxygen. Okay, that's kind of pretty much most of the variations on that Avogadro's number, Avogadro's constant that I can think of off the top of my head. If you come up against any problems that you find too much of a challenge, please feel free to ask.